Hello everyone. Welcome back to my channel. This is Sakshi and today we are going to solve all paths from source to target from LeetCode. Let's have a look at the problem statement first. Given a directed acyclic graph of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1 and return them in any order. Okay, first of all, what is the directed acyclic graph? Directed means that the edges are directed from one node to another, and acyclic means that the graph does not contain any cycles. For example, take example 1. So graph of 0 here is 1, 2, which means there is an edge from 0 to 1 and from 0 to 2. Then graph of 1 is 3. That means there is an edge from 1 to 3. Then graph of 2 is also 3. There is an edge from 2 to 3. And graph of 3 is empty. That means there is no edge originating from node 3. Now to solve this problem, we'll actually follow 3 simple steps. Firstly, we'll look at the recursion tree. Then we'll look at the implementation of the solution. Then we'll have a look at the time and space complexity analysis. So going on to the recursion tree. I'm taking this example. This is actually example 2 from the problem. So this has 5 nodes and we have some edges here. I've drawn a recursion tree for this. So this just means that from node 0, we have 1, 3, 4 edges. Then we have from 1, we have 2, 3, 4 and so on. What if we want to solve this problem for this particular recursion tree? We will start from 0. And from 0, we'll see from where can we go from 0. We can go to 0, 1. And from 1, where can we go? We can go to 0, 2. Sorry, 1, 2. Then from 2, we can go to 0, 1, 2, to 3. Now from 3, we can go to 4. So 0, 1, 2, 3, and 4. Since 4 is our destination, we got our solution 1. And after this, we'll pop out 4. We'll go back to 0, 1, 2, 3. Now at 3, we know that we can't go any further from 3. We have already reached 4. So we'll go back to 0, 1, 2. Now we are here, 0, 1, 2. And 0, 1, 2, we have already gone through this path. So we know that we can't go anywhere else. So we'll go to 0, 1. Now we are here, 0, 1. From 0, 1, we have already gone through this path. So now we'll go through 0, 1, 3, 4. So from 0, 1, we can go to 0, 1, and now 3. Okay. From 3, we can go to 0, 1, 4. And since 4 is the destination, we got our solution 2. Now we go back to 0, 1, 3. And since we know that we can't go anywhere else from here, so we'll go back up to 0, 1. And from 0, 1, one thing is left. We can go to 0, 4. So 0, 1, 4. Okay. And this was 0, 1, 3, 4. So this is our solution 3 because 4 is the destination and we have reached there. Now from 0, 1, 4, we'll go back to 0, 1. And now we have traversed through all these paths. So we'll go up. We'll go to 0. From 0, we have traversed through this tree. We'll go to 0, 3. So 0, 3. Now from 0, 3, we can go to 0, 3, 4. Since 4 is the destination, we got solution number 4. Now from 0, 3, 4, we go back to 3. And then from 3, we know we can't go anywhere else. So we go back to 0. Now from 0, only one path is left, which is 0, 4. And since 4 is the destination, we got our solution number 5. So these are the 5 solutions to this problem. Basically, these are the 5 paths from source 0 to destination 4. Okay, this was the recursion tree. Now let's look at the implementation. We'll just implement this exact logic in this code. Okay, So we'll need a function where we'll pass on the graph which is given. Okay. We need these vectors, right? So we will have vector int temp, and we obviously need a vector of vectors to store the temp vectors, which will be our final result. Okay. We need a current position and we need a destination. Now, what are we doing here? For every node, we are looking at its adjacent nodes, and we are like repeating the same logic for those nodes, right? So how do we get the adjacent nodes? We will go to I less than graph of current of current dot size I plus plus, and we will insert this new node into temp. Then we will call the DFS function for this temp. So graph will remain the same. Temp we have already updated. Then RET vector. Now current is graph of current of I, the current node, and destination remains the same. And since when we reach the solution or when we are done with this, we go back one step, right? So basically we pop one item. So we will pop one item and return. Now what is missing in this piece of code? We don't have a base condition. What is the base condition? The condition where we will insert temp into RET vector. When do we insert? When do we declare that we have found a solution? When we reach the destination. So basically, if current is equal to destination, that means we will just push temp into the RET vector and we will return. So this is our recursive function. Now to call this recursive function, we will need a result vector. We will need a temp vector. Also, we'll start from 0. So we need to insert 0 in temp before calling DFS. DFS graph, okay, temp RET, current position will start from 0 and end at n minus 1. Now we don't have n yet. How do we calculate n? N is the size of graph. Okay. And we've got RET. We'll just return. Let's run this. Okay, this is accepted. Let me try and submit it. Okay, this works. Now let's look at the space and time complexity of this function. Okay, firstly, this RET vector. This is a result vector, so we don't include it in the space complexity analysis. Then we look at the temp vector. The maximum size of the temp vector can be order n, because it is possible that we have all the nodes in the path. So in that case, it will be order n. Okay. Also, we have a recursion stack. So to get the space complexity of the recursion stack, we can like get it from the depth of the recursion tree. So maximum depth of the recursion tree can be n, which is n is the number of nodes, which is also order n. So order n from recursion stack, order n from temp. So the total space complexity is order n. Now coming to the time complexity. Time complexity of a recursive algorithm is the time complexity of a recursive function into the number of recursive calls. So if we look at this one recursive call, the time complexity of this if condition is order n, because the maximum space complexity of temp is order n, and we are pushing temp into RET, which is order n time complexity. And if we look at this for loop, so this graph of current dot size, the maximum value of this can be n minus 1. In this will be when a node has n minus 1 edges attached to it. So there are n minus 1 directed edges from that node. In that case, this will be n minus 1. So we can say that this is order of n, and this if condition is also order of n. So the time complexity of one recursive call is order n. Let me tell you, the number of recursive calls are 2 to power n. To explain this, I'll actually have to uh, create another video and I'll explain this thoroughly. But for now, this time complexity of this algorithm is n into 2 to power n. Now, if you like this video, please like, share, and subscribe. And if you have any comments, please leave them in the comment section below. See you in the next video. Bye-bye.